What is machining? Machining is a subtractive manufacturing process. It shapes a part by removing unwanted material rather than adding it. A cutting tool engages a solid block of material called the workpiece and shears away layers until the desired geometry remains. It is most common way to turn raw stock, metal, plastic or composite into precise, dimensionally accurate parts. Cutting speed, denoted by VC, is defined as the linear velocity of the cutting edge relative to the surface of the workpiece. It's expressed in meters per minute or surface feet per minute in imperial units. The governing relationship is Pc is equal to pi into d into n divided by 1000, where d is workpiece diameter in millimeters and n is the spindle speed in revolutions per minute. This is critical distinction for any machinist. Cutting speed is not the same as spindle RPM. RPM is rotational rate. Cutting speed is the surface velocity. For fixed RPM, a larger diameter workpiece produces a proportionally higher cutting speed at the tool workpiece interface because the surface travels a longer circumferential distance per revolution. The practical takeaway: cutting speed selection is fundamentally a trade off between production rate and tool degradation rate, and it's disproportionately sensitive to small increase, a relationship we will return to when we discuss tool life. Feed rate, denoted F, is the distance the cutting tool advances relative to the workpiece per revolution, expressed in millimeters per revolution or per tooth for multi-point tool like milling cutters where it's denoted FZ. Feed rate has a direct quantifiable relationship with surface roughness. For a single point returning operation, the theoretical surface roughness is approximated. While finishing passes drop, feed substantially to meet surface finish tolerances. Formed chip thickness, which directly affects the cutting force. Feed rate selection, therefore, balances three constraints simultaneously: the surface finish specifications, the cutting force limits of the setup, including fixture rigidity and part deflection, and the minimum chip thickness threshold of the tool geometry in use. Depth of cut, denoted D, is the radial or axial engagement of the tool in the workpiece per pass measured in millimeters. Combined with cutting speed and feed rate, depth of cut determines material removal rate. MRR is equal to VC into F into D. Depth of cut scales removal rate linearly identically to feed rate, but unlike feed, depth of the cut has an outsized effect on cutting force, magnified magnitude, and on system dynamics. Increasing depth of cut increases the engaged length of the cutting edge, which increases force roughly proportionally, and that force translates directly into the tool deflection, workpiece deflection, and spindle loads. Roughing operations use high depth of cut to remove bulk material efficiently, typically constrained by machine horsepower and setup rigidity rather than tool wear directly. Finishing operations use shallow depth of cut, often less than half a meter, both to meet dimensional tolerances and to minimize the force induced deflection that would otherwise compromise accuracy. This is the analogical way to understand the cutting parameters. Here, in this situation, slicing bread, cutting speed is the this is what the knife is doing. It is the speed of the knife as it moves straight down to make the cut. And feed rate, this is what the bread is doing. It is the step by step movement of the bread shifting forward to set up the next slice. And depth of cut, this is the thickness of the slice. It is the exact amount of material the knife has to cut through in the single pass. This is the analogical way to understand these parameters. And another fourth parameter is tool life. To understand uh, tool life, we have to uh, merge the cutting speed and feed rate and depth of cut and how bread is strong and how knife has to be strong to slice the bread. Tool life and Taylor's equation. Now here the part that actually matters for keeping your tool alive. Taylor figured out the relationship between speed and how fast a tool dies. It written as V into T power n is equal to C. V is the cutting speed, T is the tool life. How many minutes before that edge goes dull and can't cut anymore? N and C are the constant that depend on the tool and the material you are cutting. N tells how uh, much the tool resists heat and wear. Yeah, high N means the tool is tough. It can take a speed increase without falling apart. A low N means it's fragile, speed up even a little, and it wears out fast.